Unit 2, Elements and Molecules, Lecture 1. Our history lesson will briefly cover some ideas from Democritus and Aristotle, a bit on Lavoisier and the law of conservation of mass. We'll talk about Joseph Proust and his law of definite proportions, and we'll do a brief introduction, or the history a little bit, of Dalton's atomic theory. Democritus and Aristotle were both Greek philosophers, and of the two, Aristotle was the more famous, though Democritus preceded Aristotle a bit. Let's start with Aristotle. Aristotle was considered the most knowledgeable human in the world at that time. It was even thought that he probably had all knowledge that existed at that point. He believed in 4 classical elements. Each of these elements had 2 properties, one of which was dominant. For example, fire was hot and dry, and I have put the dominant characteristic in caps. Earth, the second element, was cold and dry. Air, hot and moist, and water, moist and cold. He showed what he believed to be a complex relationship among those 4 elements. But the most important aspect of his concept was the idea of change, and these 4 elements could gradually change from one to another by changing particularly the predominant property. Further, he believed that all matter contained the 4 elements in different proportions. And since all matter contained the 4 elements in different proportions, and these 4 elements could change from one another, it would be possible to convert lead to gold, as was his philosophy. He was very opposed to the atomist concept that we're going to hear about with Democritus, and he was opposed because that concept did not account for the cause of original motion of basic particles. Oh well, let's go on. Democritus was a firm believer, a firm advocate of the atomist concept, the concept of material being made of an atom. He was strongly influenced by Leucippus and Epicurus, who actually developed the basics of that concept. Now, he really thought that all atoms were the same, except for the way they connected, their connectivity type and extent. He thought they had hooks and eyes, or balls and sockets, that bound them together to different extents, thus producing strong metals which were locked tightly together. Water atoms that were atoms attached less securely, hence were smooth and slippery. Salt atoms that were attached in such a way that they were sharp and angular. And air atoms that were not attached well at all, hardly attached at all, and thence were light and airy. In other words, it was not what they were made of, it was how they were connected that determined what they were. So lead and iron and water were all the same atoms, connected differently. Well, neither the theories of Democritus nor Aristotle was based on scientific evidence. However, the atomist model proposed by Democritus is a hypothesis that's probably more related to our current thinking than were the 4 elements of Aristotle. To study the law of conservation of mass, we really must mention at least 2 early chemists, Robert Boyle and Antoine Lavoisier. Robert Boyle was considered to be the first chemist to engage in quantitative work. Specifically, he measured and noted the relationship between the pressure and volume of air. Although he held on to some of the alchemist concepts, such as converting base metals into gold, he was actually the end of the alchemist period. His work was published in The Skeptical Chemist in 1661. However, it was the work of Antoine Lavoisier that moved chemistry more firmly into the quantitative science arena, when 100 years after Boyle, Lavoisier invented a balance that permitted him to carefully weigh reactants and products of chemical reactions. Hence, he concluded that mass is constant in a chemical reaction. In other words, matter is neither created nor destroyed in the reaction process, and he could look to his data for strong support. The law of definite proportions was brought to us in early 1794 by Joseph Proust, who published a paper showing that the copper carbonate he produced in his lab was the same as the naturally occurring copper carbonate. Through this and several related experiments, he concluded that compounds have the same proportions by weight of the elements involved, regardless of the source. His law of definite proportions was not accepted until 1811. People just thought, oh, that can't be. Well, you may be interested in knowing that the law is not entirely true. There are several compounds that do not follow this law, but oh, that is a lecture for another day. Fascinated with the work of Antoine Lavoisier and Joseph Proust, Dalton performed his own studies, particularly noting that carbon and oxygen combine to make two different compounds. One of these compounds contained exactly twice as much oxygen as the other compound per equivalent amount of carbon. This led him to the law of multiple proportions and thence to his atomic theory. And here you see some of the representations for atoms that he used at the time. His idea was that elements consist of tiny particles which he called atoms, which of course he got from Democritus. Further, all atoms of the same element were the same in that they have the same mass. But elements differ from each other, as indicated by their having different masses, thus having different characteristics. Compounds are composed of atoms of different elements hooked together in some manner, and always in a fixed ratio of atoms. And chemical reactions occur as these atoms rearrange, combining in a different arrangement with other atoms. And so therefore atoms are neither created nor destroyed during the reaction process. It was a brilliant deduction. Do you wonder how John Dalton was able to make accurate measurements of mass in his experiments? Well, he probably had a balance of this type. Balances of this particular style made their appearance in the late 1700s, and since Dalton died in 1844, he probably had one of these. This particular balance was built in 1890 along the same designs as the type that probably would have been used by Dalton and other chemists of that period. Let me show you some of its features. First of all, it is in a case of glass so that you can see inside of it, but air currents will not cause the pans to swing back and forth. How would the chemist work in here? Well, they would open this, and there was a latch here that would hold the window open while they were adding weights or adding materials to the balance, and then the lever could be pressed and the window lowered again. But for our purposes, I'm going to remove the window so that I don't have to worry about hitting it or something of that type. Now, one of the first things that had to be done was the balance had to be level. In order to balance, because if the balance were not level, then the pin would not swing regularly across the front and the weights would not be accurate. Today, or in the 1900s, the popular way to do this was to level it, was to have an air bubble in a little vial of liquid here. But they didn't use that. What they used at the time of Dalton was a plumb bob. Now, I don't know if you can see the plumb bob or not, but it's right here. It is that swinging piece right there. That's your plumb bob. Do you see it swinging there? and it needed to line up exactly with a point right below it. And when it did, they knew the balance was level. In order to get the balance level, they would adjust the screws on the legs to raise and lower each side, or both to raise and lower the front. They would then place the item to be weighed on one side and the weights on the other. Now, the weights generally ran from something like 500 grams, like this, down to very, very small ones, like for possibly 1 gram, like this tiny one right here. Some of the more modern ones, and I don't know if Dalton had them this small or not, some of the more modern ones had tiny little pieces of material that weighed 5 milligrams, 10 milligrams, 20 milligrams, 50 milligrams, 100 milligrams, and 200 milligrams. There were even some that very possibly weighed different amounts, but this is what I have. For example, here's a 200 milligram piece of metal. It's engraved on there. And they would place the material to be weighed on one side, and they would begin adding weights. Now, how did they keep the pans from swinging? They used a dampening device right here. And this dampening device allowed the pans to sit on the bottom. And then when they were ready to weigh, they would lift the beam right here by moving this lever. Watch that beam come up. And then the pans would be free to swing. Now, you had to be very, very careful with this device, because those finely honed knife edges up here in the beam were very sensitive to any changes, and you didn't want to bang them around and notch those beams. So you would rest the balance, and you would change the masses over here, and then you would check again to see if it were being weighed right. Balances developed in the later 1900s had a platinum rider that moved along the beam to give even greater degree of accuracy and a greater degree of sensitivity. Well, I want to show you the knife edges, and to do that, I'm going to have to take the balance apart. So I'm going to reach up here and remove the pans, and then bring out the beam. Now, I want you to notice on this beam that there is a triangular area right here. And this triangular area is the knife edge. The knife edge, probably in Dalton's time, would have been made of steel, but the more modern ones were made of sapphire or agates. So folks, let me explain then. You should not ever think that these chemists and physicists were lacking in ingenuity in designing the equipment that allowed them to make many of the measurements and hence the observations that they made. In this section, entitled Atoms and Isotopes, we're going to talk about atomic notation. We will discuss relative weights, what they mean, how we get them. We will talk about isotopes and the role that they play in the relative weights. And we will talk about the mass spectrometer, the device that is used to help us determine these relative weights. And we'll wrap up on this section by calculating some atomic weights from the information that we have gained. For atomic notation, let's start with copper 64. Now, this number right here is the atomic number, the number of protons in the nucleus of the atom. This number is the atomic mass number, which is the number of protons and neutrons together. Sometimes protons and neutrons are referred to as nucleons. What tells us what the element is? The atomic number. It is the number of protons that defines the element. Now look at this. If we look at the atomic mass, or the atomic weight, that we see on the periodic table or that we look up somewhere, It is 63.929765. Notice that is a little bit less than its atomic mass number. This happens to be its relative weight. Well, if it's a relative weight, it's got to be relative to something. So what's the standard? Well, the standard that we use is carbon-12. And carbon-12 has a mass of 12. It has a mass of 12 because that's what we said it was going to be. That is its assigned weight. And the atomic weights of all isotopes are in comparison to carbon-12. Do you understand isotopes? What are they? Well, consider these three isotopes of magnesium. Now, these are the three naturally occurring isotopes of magnesium. These are not the man-made ones. We have made magnesium-28 and magnesium-23 and a host of others, but this is not considering those. This is considering the three that occur naturally. Where are they alike? Well, they are alike in the atomic number, which is the number of protons, and that has to be that way. Remember, it is the number of protons, the atomic number, that defines what the element is. Okay, where do they differ? They differ here in the atomic mass number, which is the sum of neutrons and protons, the number of nucleons, if you recall. Therefore, the isotopes differ by atomic mass number and the number of neutrons, but are the same with regard to the atomic number and the number of protons. What are these values? These are their relative weights when compared to carbon-12, the most common isotope of carbon. And look, what are these values? These are the percent of their natural occurrence, the frequency of their natural occurrence, if you will. Let's see how we determine these values. It used to be quite a process of chemical reactions and weighing reactants and products and comparing them and so forth. The process now is much, much more definitive. We use a device called a mass spectrometer, which sometimes we call a mass spec. And the mass spec will allow us to very accurately determine both the relative weight of an isotope and its frequency of occurrence. Now, I'm going to give you a simplified version of the sample is placed in the sample chamber here, where it is vaporized and ionized. It then passes through this exit slit at a very high rate of speed, moving down the tube toward those magnetic plates. Now, it's going to be repelled by the positive plate and attracted by the negative plate. So by adjusting the strength of those magnetic plates, or adjusting the magnetic field strength, we can adjust or change the path that the isotope is taking. And you see that right here at the exit slit, the way we have it adjusted right now, one of the isotopes is coming through. But by increasing or decreasing that magnetic field strength, we can move around and allow a different isotope to come through. Electrons pass through the magnesium vapor, creating this reaction. The magnesium ions then are going to pass through the exit slit at a high rate of speed down this tube toward the exit slit. Now notice, depending on the mass of these particular ions, they will come through at the exit slit or not. And what we may have to do is adjust the magnetic field strength to get the various ones to pass through. It passes through the exit slit to a detector where we can determine by the relative heights the relative quantities of these that are produced and their relative weights. Now let's see how we use this to calculate atomic weights. Atomic weights for the periodic table are weighted averages, and what this means is they use both the weight and the frequency of occurrence to see how much or to see what portion of the weight each isotope contributes to the total. So you have to use both the weight and the percent occurrence when you do this calculation. Let me show you how. Let's look at magnesium. If it has these three natural isotopes, let's find the sum of the contributions of each isotope. Let's start with the magnesium 24, which weighs 23.985042 AMU, if you will. And it occurs 78.9903% of the time. So we convert the percent to a decimal, multiply it, and that gives us the amount that that particular ion contributes to the mass of what we're going to be recording. We do the same thing to magnesium 25 and the same thing to magnesium 26. Now we know the amount that each one of the isotopes contributes to the average amount, or the atomic weight if you will, and that gives us the atomic weight of 24.3050. And this is the weight that we will use on the periodic table. Now, do you have an idea of how it works? Remember, it is the percent occurrence times the atomic weight, or the relative weight of each one of the individual isotopes to give us the amount that that particular isotope contributes to the whole. We do this, we add those up, and that gives us our periodic table weight. We will begin Lecture 2 by covering some problems that are going to utilize just this kind of information. So be sure you understand how all of this information came together before we begin the next lecture. A better way to teach and learn chemistry.